If you were a chemist in the late 19th century and you wanted to turn an ester into an alcohol, you had a serious problem. This was decades before the discovery of powerful reagents like lithium aluminum hydride. Your options were limited and the chemistry was stubborn.
But in 1903, Louis Bouveault and Gustave Blanc discovered a clever workaround. They found a way to force electrons into a molecule using nothing but metallic sodium and a bit of alcohol. Today, we call this the Bouveault-Blanc reduction.
Let's look at our starting point, an ester. You can see the carbonyl group here, that carbon double bonded to an oxygen sitting next to another oxygen atom. To turn this into a primary alcohol, we essentially need to add 4 hydrogen atoms and break that carbon-oxygen single bond.
But how do we get there? It starts with a piece of solid sodium metal. Imagine the surface of this metal as a sea of restless electrons. As we drop a piece into our solution, a single electron jumps from the sodium surface onto the carbonyl carbon. Notice what happens to the bond. That double bond pops open. We now have what's called a radical anion. It's an unstable, high-energy state where the oxygen carries a negative charge and the carbon has a lonely, unpaired electron. Now this is where the solvent comes in. We've used an alcohol, like ethanol, as our proton source. High-energy intermediates don't stay lonely for long. This radical anion quickly grabs a proton from the ethanol. Look at the carbon now. It's no longer an anion, but it's still a radical. It's still hungry for another electron to feel stable. And here's the key insight. Because the carbon is still a radical, it can take a second electron from another sodium atom. Watch as this second electron joins the first one, creating a new lone pair on the carbon. Now we have an even more reactive species called an alkoxide. At this point, the molecule undergoes a transformation called an elimination. That OR group, the alkoxy part of the original ester, is kicked out. As it leaves, the carbon creates a new double bond with the oxygen. Wait a second, look at the screen. What does that look like? That's an aldehyde. But we aren't done yet. In these reaction conditions, an aldehyde is even more reactive than the ester we started with. The whole process repeats itself. A third electron from sodium attacks the carbon. Another proton is snatched from the ethanol. A fourth electron jumps in, and one final proton is grabbed. As we finish the sequence, we arrive at our final destination, a primary alcohol. It's easy to take modern reagents for granted, but the Bouveault-Blanc reduction is a beautiful reminder of how classic chemistry works. It doesn't rely on complex hydride delivery. It relies on the raw power of single electrons moving one by one to rebuild a molecule. The next time you see a metal surface, don't just think of it as a solid object. Think of it as a reservoir of potential, waiting for the right moment to push a molecule toward a new identity.